Hello and welcome to Minerals, Rocks, and Fossil Talks. I'm your geology teacher, Jen, and it's time for Monday Musings. So last week we talked about Pangea, just like what Pangea was and how it came together and that it wasn't the only supercontinent that ever existed and all this stuff. Today we're going to talk about the climate and megamonsoons. So let's talk about monsoons. What is a monsoon? A monsoon is traditionally a seasonal reversing wind accompanied by corresponding changes in precipitation, but now used to describe seasonal changes in atmospheric circulation and precipitation associated with annual latitudinal oscillation of the intertropical convergence zone, specifically between its limits to the north and south of the equator. Lots of big words, and it's not gonna really get simpler. I'm gonna try to make it as simple as I can. Okay, so usually the term monsoon is used to refer to the rainy phase of a seasonally changing pattern, although technically a monsoon is both the rainy and the dry season. The term is also used to describe locally heavy but short-term rains. In North America, monsoons are experienced in the southwestern U.S. I grew up with monsoon rains, and it ruined my birthday parties every year because I have a summer birthday and I desperately wanted to have a pool party, and those damn monsoons brought thunderstorms that always ruined it. Every time. I can count on one hand the number of times it has not rained on my birthday, and it is like 4, maybe 5 at this point. Literally one hand. Every year. Every year it rains. It's awful. But only if you are a child wanting to have a pool party. Otherwise, those rains are desperately needed. But to try and kind of sum this up, so during the summer, the ocean brings moisture-laden air landward, and high mountains force that air upward, where it cools rapidly, causing it to condense and drop large amounts of rain, as this diagram shows. In the winter, the land is cooler than the ocean, and so it sends the water out to the ocean, where the rains will happen there instead. Make sense so far? Cool. Hopefully. So Pangea also experienced monsoons, but on a larger scale. Monsoon circulations, defined as a seasonal reversal of winds, exhibit large shifts in precipitation patterns across the impacted region. Monsoons are therefore characterized by 2 primary seasons, the rainy and the dry. They are induced by the presence of at least one large landmass and large body of water in close proximity to each other. So the biggest monsoons we have these days are in India, because Asia is a huge continent, huge landmass, and then you have the massive Himalayan mountains blocking the moisture from going any further than India and causing the water to drop there. Pangea was a supercontinent with a huge mountain range right in the middle that was comparable to our Himalayas, as we talked about last week. So we also have our land masses kind of wrapping around this Tethys Ocean, and this is this shape, and what's going on here is going to characterize our mega monsoons. Okay, so let's get into some history. The concept of a Pangean megamonsoon circulation was first proposed in 1973. The evaporites in the geologic record suggest vast and extensive regions of persistent dry conditions near the Pangean center, serving as the initial evidence for the theory's dissemination. The interior of the supercontinent, especially the eastern portion, would have been extremely dry, as the hemispheric pressure systems driving the circulation would have diverted nearly all atmospheric moisture away from that region. Thank you, Central Pangean Mountains. The later indication of a monsoon-driven climate was acquired via the examination of coal deposits along the exterior portions of the continent. The presence of both features in the geologic record suggests monsoonal circulations. Okay? Because coal is going to come from plants, and plants need lots of water. Cool. As the theory of the Pangaean megamonsoon began to increase in credibility, paleoclimatologists predicted the climatological impacts of the circulation to ascertain whether observations and models supported the hypothesis. The general consensus listed 4 primary signs that needed to be present to validate the existence of the megamonsoon. The first is that the lithologic, or rock indicators of seasonality, should span broad distances along the Pangaean coast. 2, evidence depicting a deviation from zonal flow regimes needed to be identified. 3, records should indicate that the equatorial regions of Pangaea would have been plagued by persistent aridity. And 4, models and geologic observations would need to demonstrate that this circulation peaked during the Triassic, not the Permian. There are reasons for that. So, in the northern hemisphere summer, when Earth's axial tilt was directed toward the sun, Laurasia would have received the most direct solar insolation, which would have yielded a broad area of warm rising air and low surface pressure over the continent. Models have suggested that this seasonal low was positioned at 35 degrees latitude. So if this line here is our 30 degrees, we're talking up here a little bit. Okay. Just above that line. In Gondwana, high pressure would have dominated, as the land would have been receiving less solar radiation and therefore experiencing cooler temperatures. So that's this lower portion. The pressure gradient force dictates that air will travel from regions of high pressure to low pressure. Therefore, that would have driven the atmospheric flow from the southern hemisphere toward Laurasia, the northern hemisphere, during which it would cross the Tethys Ocean. Water from the Tethys would evaporate into the air mass, and eventually that air mass would reach the coast of Laurasia, and it would result in large, immense amounts of precipitation as it hit that Pangaean mountain range. Models estimate the globally average precipitation to equal roughly 1,000 millimeters per year, with coastal regions receiving upwards of 8 millimeters of rain each day during the rainy season. As the atmospheric flow was directed away from the Gondwana high-pressure system, surface winds would have diverged, producing clear and very dry conditions across the southern hemisphere. Now, several studies have indicated that the circulation was so intense during the Triassic, it would have been capable of reversing part of the predominantly easterly global wind flow, and so westerly winds impacted the western coast. That worked to maximize surface convergence and increase seasonality along the coasts of each continent. During the northern hemisphere winter, when Earth's tilt was directed away from the sun, the circulation reversed as the area of maximum solar insolation shifted toward the southern hemisphere. Air then traveled from Laurasia, a region of high pressure, across the Tethys Ocean to Gondwana, a region of low pressure. Moisture advection toward the southern hemisphere would have fueled heavy precipitation along the Gondwanan coast, while Laurasia remained very dry. So it was a back and forth, and back and forth. Okay? Hopefully that makes sense. I know it's a lot of sciencey words to be thrown at you, but I tried as best as I could to make it simple. Hopefully it makes sense. And thanks for coming to today's lesson. Make sure you tune into tomorrow for some fun monsoon trivia, and I will fossilize you later.